Atomic radius essentially compares the size of different atoms or elements. Generally, atomic radius increases as you move left and down the periodic table. This is because electrons occupy higher levels and the electron shielding lessens the pull of the positively charged nucleus. This results in a greater distance from the nucleus and increases the size of the atom. As you move right on the periodic table, the number of protons and electrons increase. However, the effect of increasing proton number is greater than that of the increasing electron number. Therefore, there is a greater nuclear charge, otherwise known as ZEF. This results in a smaller atom.
Ionization energy and electronegativity are opposites. Ionization energy is the energy required to remove an electron from the outermost orbital of an atom, whereas electronegativity describes the atom's ability to attract an electron, almost like Thor's hammer is attracted to Thor. Both ionization energy and electronegativity increase as you go up and across the periodic table left to right. On the right side of the periodic table, elements are closer to completely filling their valence shell by forming anions, whereas on the left side, they are more likely to lose electrons and form cations. The atom pictured here has a perfect octet and is consequently stable, resulting in a much higher ionization energy than this atom, which only has one valence electron. Since it wants to become stable, it requires much less energy to remove it.
All elements want to fill their outer shell to form a stable noble gas electron configuration. Any element that is super close to getting that full outer shell is the most electronegative. These are elements which only need one or two more electrons to fill up their shell. Remember, noble gases have negligible electronegativities because they are happy with their full octet, so fluorine is the most electronegative element. Ionization energy and electronegativity decrease as you move down the periodic table because electron shielding increases with the addition of orbitals. Since the electrons are farther from the nucleus, the attraction is reduced between the protons and electrons, making the atom more apt to giving away electrons.
However, there are a few exceptions. According to the trend, Group 3's first ionization energy is expected to be larger than Group 2, but the opposite is actually the case. For example, boron, Group 3, is expected to have a larger ionization energy than beryllium, but beryllium's is larger. This is because 1, it is stable with a completely filled outermost s orbital, whereas boron is 1 electron beyond stable, and 2, the p orbital has a more complex shape than the s orbital, so sometimes the electrons in the p orbital of boron are farther from the nucleus, making it easier to remove. The next exception deals with groups 15 and 16. According to the trend, group 16's first ionization energy is expected to be larger than group 15, but group 15 is larger. For example, oxygen is expected to have a larger first ionization energy than nitrogen, but nitrogen's is larger. This is because 1, oxygen is stable with a half-filled p orbital, whereas nitrogen, like boron, is 1 electron beyond stable, and 2, the electron in oxygen is being repelled by the paired electron, so it's slightly easier to remove than the last electron in nitrogen.